Hello students, welcome to Chemistry at JP's Academy and I am Nitin sir. In today's one short lecture, we will complete chemical equilibrium and ionic equilibrium, starting from the very basics of what are reversible reaction right up to students pH indicator. Before we start the lecture, I request everyone to please like the video, subscribe and share it with your friends so that they can quickly revise this within 45 minutes whenever they have any exam. So let's start with the lecture, students. What exactly is a reversible reaction? A reversible reaction is a reaction which proceeds in both directions, forward as well as backward. So let's say we have a reversible reaction. Now, the speed or the rate of any reaction according to the law of mass action is directly proportional to the product of the active mass of the reactant raised to their stoichiometry. So students, I can write that the rate of forward reaction or the speed of forward reaction is equal to the rate constant Kf into reactant, the product of molar concentration of reactant raised to their coefficient, and the same for backward reaction. Remember students, Kf and Kb are called as rate constants or velocity constants and they're dependent only on temperature. When we reach equilibrium, the rate of forward reaction becomes equal to the rate of backward reaction. And when we equate this, we get the expression for equilibrium constant, which is given by capital K. Equilibrium constant is the product of, it is equal to the ratio of the product of molar concentration or the active masses of product raised to the stoichiometric coefficient to the reactant raised to the stoichiometry. The equilibrium constant in terms of concentration is expressed as Kc. So the law of chemical equilibrium says that at a given temperature, if I want to know what is Kc, it is the product of concentration of products raised to their stoichiometric coefficient divided by the product of concentration of the reactant raised to their stoichiometry, and this has a constant value at a constant temperature. Moving ahead, when we express the same parameters but in terms of pressure, equilibrium constant is expressed as Kp. So Kp is the equilibrium constant when all the active masses are in units of pressure, that is atm. The expression for Kp is given by the product of partial pressure of the gases raised to their stoichiometry upon the product of partial pressure of the reactant raised to their stoichiometric coefficient. Now, the relation between Kc and Kp is given by the expression Kp is equal to Kc into Rt raised to delta Mg, where delta Mg stands for the number of moles of gaseous products minus the number of moles of gaseous reactants. Moving ahead, we have two types of equilibria, students: homogeneous equilibria and heterogeneous. Let's understand what they actually mean. Homogeneous equilibria is when all reactants and products are in the same phase. ये reactions अगर आप देखें, you will observe that all the reactant and product are in the same phase. What is heterogeneous equilibria? Equilibrium in which equilibrium where you have multiple phase, that is equilibrium in a system having more than one phase. For example, over here from liquid to gas, this is equilibrium between the liquid phase and the vapor phase. Now students, we have to be very careful when we write the equilibrium expression. For example, in this expression CaCO3 solid in equilibrium with Ca solid, CaO solid plus CO2, or we can say that the thermal decomposition of calcium carbonate. When we write the expression for Kc, if you see that the final expression has no CaO or CaCO3, what we need to really remember here, students, is that molar concentration of a pure solid or a pure liquid remains constant and they will not be part of the equilibrium expression, and hence the molar concentration of CaCO3 and CaO will not be considered in the equation and it is considered constant. So whenever we are writing equilibrium expression, please note that solids and liquids will not be part of the expression. Next, some uses of equilibrium constant K. Now, the most important use is to predict the extent of any reaction. If the value of equilibrium constant is greater than 10 to the power 3, we say that the reaction has reached almost completion and where products are in majority. If the value of equilibrium constant is very small, less than 10 raised to minus 3, we say that the reaction hardly proceeds at all and reactants are in majority. And if the value is somewhere between 10 raised to minus 3 to 10 raised to 3, we say that the reaction at equilibrium, both the reactants and products will be present in considerable quantity. The second important application is it helps us also decide the direction of reaction, in which direction is the reaction moving. For that, students, we need a very important parameter which is called as QC, which is reaction quotient. Let's understand what's the difference between QC, reaction quotient, and Kc, equilibrium constant. Reaction quotient is defined in exactly the same way as equilibrium constant, except that the values we take over here are not necessarily equilibrium values. It means the concentration of products, the active mass of products or the active mass of reactant that we have, it may or may not be the actual value that they have when they reach equilibrium. So when we substitute these values, if the reaction quotient is less than the equilibrium constant, then we say that the reaction has to the equilibrium is not yet reached, that the reaction will proceed in forward direction. If the value of the reaction quotient is greater than the equilibrium constant, we say that the reaction is crossed or the reaction has to move in backward direction for equilibrium. And if both the values are equal, we say that the net reaction is at equilibrium. Now, I have given an example here, students, which you can solve in order to identify in which direction will the reaction proceed. So make sure you please solve this. Now, the next topic that we have, people, is calculating equilibrium concentration or calculating the expression for equilibrium concentration for different reactions. This is very important, students, from a numerical perspective, where they will give you a reaction, they'll give you values, and आपको या तो expression calculate करना होगा, or you'll have to calculate some value or concentration at equilibrium. So let's take a very simple example where what we have done is we have the dissociation of dinitrogen pentoxide, N2O4 का dissociation लिखा है, N2O4 in equilibrium with 2NO2, nitrogen dioxide. Let's say the initial number of moles is A and there are no moles here. Number of moles at equilibrium. As the reaction starts, some of the moles of reactant will convert into products. Let that be X. Therefore, number of moles at equilibrium will be A minus X and number of moles of NO2 will become 2X. So now when we write the equilibrium expression, since this was in moles, we divide by volume to get molarity. So the molar concentration of N2O4 is the number of moles A minus X by V, and for NO2 it is 2X by V. On applying the law of mass action and law of equilibrium, we get the expression for Kc, which is NO2 raised to 2 upon N2O4, and when we substitute the molar concentration, students, we get the expression for Kc. Depending upon in the numerical कुछ values दिए होंगे and you'll have to find the value for Kc. Similarly, to find Kp, we need the partial pressure of NO2 upon partial pressure of N2O4. But partial pressure according to Dalton's law is the mole fraction of the component into total pressure. So that will become mole fraction of NO2 into total pressure, the whole square upon mole fraction of N2O4 into total pressure. How do we find the mole fraction of NO2? To find mole fraction of NO2, we need number of moles of NO2 upon total number of moles. Number of moles of NO2 here is 2x and total number of moles will be a minus x plus 2x, that is a plus x. That helps us find mole fraction of NO2, mole fraction of N2O4, and when we substitute the expression over here, we get the expression for Kp. Similarly, students, you can do these examples where you can find the relation between Kc Kp, where you can find the expression for Kc, you can find the expression for Kp, and numericals usually come around these equations. Moving ahead, next very important topic, what is the relation between equilibrium constant K, reaction quotient Q, and Gibbs free energy? So the relation between reaction quotient and Gibbs energy, delta G is delta G naught plus RT ln of Q, or delta G is delta G naught plus 2.303 RT log of Q to the base 10. We know that at equilibrium delta G is 0. So when you put 0 over here, a reaction quotient, which means we have reached equilibrium, so that is K. So delta G naught का expression बन जाता है, delta G naught is minus RT ln of K. या in terms of log 10 लिखना हो, so 2.303 RT log of K to the base 10. We know that, students, according to thermodynamics, for any process to be spontaneous, Gibbs free energy should be negative. So if delta G naught is negative, equilibrium constant K will be greater than 1, and it's a spontaneous reaction proceeding in forward direction. Similarly, if delta G naught is greater than 0, non-spontaneous process K, equilibrium constant K will be less than 1, and it will be a non-spontaneous reaction proceeding in backward direction. Next, students, we have which are the different factors which affect equilibrium and Le-Chatelier's principle. Now, a system which is in equilibrium can be affected by these parameters, which is a change in concentration, a change in pressure or a change in volume, change in temperature, addition of an inert gas, and addition of catalyst. Let's tackle each and every one of these. So, सबसे पहले change in concentration. Students, if you increase the concentration of reactant, the equilibrium will shift in forward direction. If you increase the concentration of product, or on addition of product, equilibrium shifts in backward direction. If you remove any reactant, if you decrease the concentration of reactant, equilibrium shifts backward. And if you increase the if you decrease the concentration of products, equilibrium shifts in forward direction. A very important point to note here, students, if you see again a thermal decomposition of CaCO3, so calcium carbonate, calcium oxide, and CO2, since these are solids, any change in concentration of CaCO3 or CaO will not change the equilibrium direction. Next, students, we have change of pressure and volume. Pressure आप increase करोगे तो volume decrease होता है, pressure decrease करोगे volume increase होता है. तो students, एक general statement we need to remember, and that statement is any increase in pressure, अगर pressure बढ़ाओ, if you increase the pressure, equilibrium will shift in that direction where there is lesser number of moles. अब हमने यहाँ पे 3 conditions लिखे हैं. First condition, where number of moles of products is more than the number of moles of reactant. If you increase the pressure, I repeat, equilibrium shifts in the direction with lesser number of moles. Lesser number of moles are on the PCl5 ka side, and hence when you increase the pressure, reaction equilibrium shifts backward. If you decrease the pressure, the equilibrium shifts forward. Same thing with volume, students. Pressure बढ़ रहा है तो volume कम होगा. They can also use volume. Now, second condition में we have more number of moles in reactant and lesser number of moles in product. In this case, again, if you increase the pressure, since the number of moles are lesser on the product side, equilibrium shifts forward, and for decrease in pressure, equilibrium shifts backward. But if the number of moles are equal, for example, H2 plus I2 in equilibrium with 2HI, same number of moles on both sides, a change in pressure or change in volume has no effect on the equilibrium. Moving ahead, next is change of temperature. Again, a general statement here, students. When the temperature of a system is increased, the equilibrium will shift in that direction where heat is absorbed. So if I have an exothermic reaction is a reaction in which heat is released. If you increase the temperature, equilibrium will shift in that direction where heat is absorbed. So if you increase the heat by increasing the temperature, equilibrium shifts backward. And if you decrease the heat, or if you decrease the temperature, equilibrium will shift in forward direction, or if heat is withdrawn by lowering temperature. Similarly, students, if it is an endothermic reaction, observe exactly opposite it will happen. You can pause the video, copy all these points, make your own short notes. Next, students, we have addition of inert gas. Addition of inert gas can be done in two different ways. It can be done at constant volume and it can be done at constant pressure. However, when it is done at constant volume, when you add an inert gas at a constant volume, please remember, students, inert gas need not always be the inert gases that we know, helium, neon, argon. It can be any gas which is not reacting with the gases present. So if it is done at constant volume, if an inert gas is added at a constant volume, there is no impact on equilibrium. The reason for that is the partial pressure of the gas remains the same, and hence there is no change in the equilibrium direction. However, if it is done at constant pressure, if equilibrium is done at constant, if addition of an inert gas is done at constant pressure, what happens is equilibrium shifts in that direction which contains greater number of moles. Let's understand the reason why this happens. When you add an inert gas at constant pressure, volume increases, and we know that if there is an increase in volume, equilibrium will shift in that direction which contains more number of moles. Finally, addition of catalyst. An addition of catalyst to a particular system has no impact on equilibrium. A catalyst does not affect a state of equilibrium, and the value of equilibrium constant remains the same. Moving ahead, students, we now start with ionic equilibrium in solution. In weak electrolytes, equilibrium is established between ionized and unionized molecule. This type of equilibrium involving ions in equilibrium is termed as ionic equilibrium. We study a new point over here, alpha. Alpha को हम बोलेंगे degree of ionization or degree of dissociation, very important, which is the ratio of number of ions dissociated or number of ions ionized upon total number of ions. For strong electrolyte, dissociation constant is 1. For weak electrolyte, it is always less than 1. Classification of electrolytes. We have three types of electrolytes. Students, we have strong electrolytes, we have acids, we have base, and we have salts. Acids and base can be further classified into Arrhenius, Bronsted and Lowry, and Lewis. Let's see one at a time. What is an acid according to Arrhenius? An acid is something which gives H plus in its solution. Base will give OH minus. What is Bronsted and Lowry acid? Bronsted and Lowry acid is acids are proton donors and base are proton acceptor. According to Lewis, what is an acid? An acid is an electron pair acceptor and a base is an electron pair donor. If you carefully observe, we get that all Bronsted base, I repeat, all Bronsted base are, all Bronsted base are Lewis base, but all Bronsted acids are not. Similarly, if anyone can give me a relation between Arrhenius acid and Lowry Bronsted acid. Similarly, what are salts? Species which have cations from base and anions from acids are known as salts. Electrolytes also can be further, students, classified as strong and weak electrolyte, which we just did. Next, some examples of Lewis acids and some examples of Lewis base. I further classified Lewis acids into simple cations, electron deficient, which we have, where you don't have 8 electrons in the outermost shell. We have central atom with empty or vacant d orbital, and compounds with multiple covalent bond. These are some examples of Lewis acids. Similarly, I've shared examples of Lewis base. Make sure you note this down because there can be integer based questions which can be asked. Next, we have What are conjugate acid-base pair? Now students, from an acid, wherever you remove an H plus, you get its conjugate base, and whenever you add an H plus to a base, you get conjugate acid. For example, over here it is HCl plus H2O. When this HCl gives H plus, it becomes Cl minus. So the HCl and Cl minus are called as conjugate acid-base pair. Remember, stronger the acid, weaker the conjugate base. Weaker the acid, stronger the conjugate base. From an acid, if you want its conjugate base, you remove an H plus, and from a base, if you want its conjugate acid, pardon me, you add an H plus. Now I want students you to complete this table. I've written some acids, write their conjugate base. I've written some base, you write their conjugate acids. In case if you're stuck on any, please let me know in the comments. Next students, we have ionization, a constant for weak acids and for weak base, Ostwald's law of dilution. So if we have a weak acid Ha on dissociation, so weak acid, this will be base, conjugate over here H3O plus and A minus. Let's say that the initial concentration for the weak acid is C. Water, as we all know, will be taken as constant. After reaching equilibrium, the concentration for the weak acid will become C minus C alpha, H plus will be C alpha, A minus will be C alpha. So when we write the expression for equilibrium constant, it is called as Ka. Ka stands for the dissociation constant of a weak acid. Larger the value of Ka, stronger the acid. Remember students, when defining this for a weak acid, Ka for a strong acid will be infinite. Now, H3O plus, the value for H3O plus is C alpha, the value for A minus is also C alpha. When you substitute that, we get the expression for Ka as alpha square C upon 1 minus alpha. For very weak acid, we can assume that the dissociation constant will be very small. So 1 minus alpha will be approximately equal to 1. We get the expression for Ka as alpha squared C. Now, students, before we move on to pH, I have also written the formulas for pH calculation. All the formulas which are boxed, please make sure you copy those, and directly you have substitution. You get very easy numericals JEE mains पे दी हुई जहाँ पे students आपको formula पता हो, आप directly formula में put करो and you can get the answer. Make sure you make good short notes out of these. Similar expressions are also present for Kb. So for example, students, Kb का expression will be in terms of base. So यहाँ पे BOH आएगा, B plus and OH minus. Instead of Ka, you will write Kb. The expression will remain same, which is alpha square C. However, instead of H plus, you'll be writing OH minus here, and instead of pH, the expression will be for POH. So let's understand what exactly is pH and pH scale. If we write the equation for auto-protolysis or self-protonation of water, where one water is donating an H plus, the other is accepting an H plus, we get an expression like this. We get this reaction. When we write the equilibrium expression for this, which is H3O plus into OH minus upon H2O into H2O, we know that students, H2O will be taken as constant. So K into H2O square, if I take the H2O into H2O to the left, all that can be replaced by one constant, which is Kw, and Kw stands for the ionic product of water. I repeat, Kw stands for the ionic product of water, which is the concentration of H plus into OH minus, which at 298 Kelvin, students, is equal to 10 to the power 14. Now when we apply the pH scale is negative logarithm of H, or you can say students, the px scale, which is negative logarithm of the function x, which is here. So in pH scale, if we apply, we get the expression pKw is equal to pH plus pOH, which is equal to 14. And pH is the negative logarithm of the concentration of H plus ions, pOH is the negative logarithm of concentration of OH minus ions, and pKw is the negative logarithm of concentration of Kw. For a conjugate acid base pair, we get the expression, students, Kw is equal to K into Kb and pKw is equal to pKa plus pKb. pH scale goes from 0 to 14. At 7, it is neutral. So when pH is 7, it is neutral. As we go from 7 to 0, or pH when it is less than 7, we say that the solution becomes more and more acidic. As we go from 7 to 14, when pH increases, we say that it is an alkaline solution. So I've written the same points here. The third and fourth point are very important. What does the third point say? The pH of pure water at its boiling point is around 6.145. As temperature increases, students, please remember pH will decrease since more ions will be produced because of dissociation. The hydroxyl ion OH minus is hydrated to give several ionic species like H3O2 minus, H5O3 3 minus, and so on. Similarly, H plus ion is further hydrated and it will give you H3O plus. How do we get the students H plus H2O? So this is your H3O plus. And if you keep on doing this H3O plus H2O, this will give you H5O2 plus, and so on and so forth. Remember, this is H plus. Even this behaves like an H plus. All these are nothing but hydrated H plus ions. Next, moving ahead, what if you have in a solution, students, two weak acids? So, for example, I have first a weak acid HA. The concentration of the weak acid is let the concentration of the weak acid be C1 and the dissociation constant of the weak acid be Ka1. I have acid 2. Let the concentration be C2 and the dissociation constant be Ka2. So remember, the H plus over here will be because of both contribution of HA as well as contribution for HB, and I have directly written the expression. If you want, students, I can also give you the derivation for this. The concentration of the H plus ions in a solution of two weak acids will be C1 alpha 1 plus C2 alpha 2, and the pH for the same can be calculated using any one of the two expression. The second expression for H plus is under root of C1 Ka1 plus C2 Ka2. Remember, students, if you have a mixture of two acids, this can be further in exam you can get a question where you have a weak acid in the presence of a strong acid. So the H plus has to be considered in case of both the acids present, or in case of polyprotic acids we have to be very careful, and that is what we have done in the next part. In case of polyprotic acids where you have more than one H plus, so let's say we have a polyprotic acid over here H3A. H3A on dissociation will give you H plus and H2A, and we have written the expression for Ka1. Similarly, H2A minus will further dissociate to give you H plus plus Ha2. But remember, students, successive dissociations will further slow down. It will be less as compared to the previous one. Ha2 further dissociates to give you H3O plus plus A3 minus, and I've written the equilibrium expression, the ionization constants for the equilibrium constants for all of them. What we need to really remember here, students, is removing proton from Ha2 minus is more challenging as compared to when you're removing it from H3A, and removing it from Ha2 minus is further more difficult, as a result of which K1 is much greater than Ka2 and much greater than K3. Higher order ionization constants are always smaller than the lower order ionization constant. Moving ahead, very important, we have common ion effect and buffer solution, in which we will first start with what exactly is common ion effect. I have, students, over here a weak acid. I have taken acetic acid, dissociation of ethanoic acid or acetic acid, I get the acetate ion and H plus. Now in this weak acid I add a salt of the same weak acid and a strong base. So I have sodium acetate over here, salt. It will dissociate to again give me acetate ion and Na plus. Now there was already an equilibrium established between CH3COH, acetate ion and H plus. The moment I add external sodium acetate, the number of CH3CO minus acetate ion increases. This disturbs the equilibrium and the amount of CH3CO minus increases. According to Le-Chatelier's principle, if the concentration of products increases, the equilibrium shifts left. The equilibrium shifts backward. So what's exactly happening over here? The suppression of a weak electrolyte, in this case, the weak electrolyte is acetic acid, on addition of a strong electrolyte, which is our sodium acetate, containing a common ion. Common ion is acetate ion. As a result of the common ion, the dissociation of an already weak acid, already weak electrolyte is further suppressed. This phenomena is called as common ion effect. Now, if I have the same weak acid, acetic acid, ethanoic acid, and the salt of weak acid plus strong base, shortcut में लिखा है WA, weak acid, SB, strong base. Now I add few drops of HCl. I add few drops of a strong acid. I know that HCl will now dissociate. The number of H plus ions will increase. As H plus ions increases, the pH will start decreasing. However, what happens is the acetate ions, the excess of acetate ions will quickly combine with H plus and will form more undissociated CH3COOH. This is how, even after adding few drops of HCl, the pH is still maintained. Now let's add few drops of base. If you add few drops of NaOH, the pH starts to increase because OH minus increases. This again disturbs the equilibrium. So what happens is, to stop this OH, we have H plus, which will combine with OH and form unionized water molecule, and the pH is maintained. And hence, what exactly is a buffer solution? A buffer solution is a solution which maintains its pH even after adding few drops of acid or base. Remember students, few drops of acid and base. This specific buffer which we have here, which is a combination of weak acid and the salt of the same weak acid with strong base, this particular buffer is called as an acidic buffer. The pH for an acidic buffer is given by this particular formula. pH is equal to pKa plus log of concentration of salt to the concentration of the acid. Next, we have types of buffer solution. Just like we studied the buffer action of an acidic buffer, students, exactly is the same as the buffer action of a basic buffer. So we have four types of buffer solution. The first buffer solution is acidic buffer, which is a combination of weak acid and a salt of weak acid with a strong base. Next, we have basic buffer, which is weak base plus a salt with the same weak base and strong acid. I've also written the formula for pOH of a basic buffer. Next, you can also make a buffer solution by making a solution of a salt containing an amphoteric ion. I've written an example for that, HCO3. And the fourth type of buffer solution that we can make is by making a solution of a salt containing a conjugate pair of weak acid and weak base. We can consider something like this. एग्जाम्पल के लिए हम इसको कंसिडर कर सकते हैं CH3COONH4. Moving ahead, students, we have something called as salt hydrolysis. So let's quickly understand what is salt hydrolysis. It is the phenomena involving the interaction of cation or anion of a salt with H plus or OH minus from water, which results into a solution which is either acidic or basic or neutral. Then it is called as salt hydrolysis. Now students, we have four types of salts. मैंने तीन ही लिखे. I'll tell you fourth वाला कौन सा है. The first type we have is strong acid, weak base, weak acid, strong base, weak acid, weak base, and the fourth type is strong acid, strong base. तो fourth type last में बताता हूँ क्यों नहीं लिखा है, आप लोग समझ जाओगे. First we have salt of strong acid, weak base. I have written some examples over here. The hydrolysis constant KH, just like we have K ionization constant, since we are performing salt hydrolysis, it is called as KH, which is hydrolysis constant, that is ionization constant. जो भी वीक है उसको डिनोमिनेटर में लिख दो, शॉर्टकट में याद रखना है। तो सॉल्ट ऑफ स्ट्रॉन्ग एसिड वीक बेस, तो बेस वीक है ना, तो KW अपॉन KB। यहाँ पे वीक एसिड है, सो KW अपॉन KA। अब यहाँ में दोनों वीक है, यू हैव वीक एसिड एंड वीक बेस, सो इट इज KW ओवर KA इनटू KB। Next, degree of hydrolysis, same expression KW upon KB, but into the concentration of the salt. KW upon K into the concentration of the salt. KW upon K into KB, यहाँ पे H will exactly be the same since it's a weak acid, weak base salt. Finally, pH के भी formula जो weak है, तो 7 minus weak base, तो 7 से कब होना चाहिए, because the final solution is going to be acidic, it's a solution of strong acid and weak base, and hence it will be 7 minus half pKb minus half log C. When we do the same for a salt of weak acid and strong base है, pH 7 से ज्यादा होगा, तो 7 plus half pKa plus half log C. And in the third case, where you have a weak acid and weak base, the formula is 7 plus half pKa minus half pKb. Now, if my acid is strong, my solution will be acidic. If my base is strong, my solution will be basic. अगर दोनों weak है, then the nature of the solution will depend upon which one is relatively stronger. If the weak acid is slightly stronger than the weak base, तो acidic होगा. If the weak base is slightly stronger than the acid, then will be basic. Same है तो neutral. Now the fourth type, which was strong acid and strong base. Students, strong acid and strong base is nothing but neutralization, and in that case hydrolysis is not valid, and for such a case pH will be 7. A simple example for that, students, can be NaCl. Make sure you copy all the formulas. Very important. If you need the derivation for this, please let me know. I'll make a very separate lecture where I will derive all the expressions. Next, students, we have is solubility equilibrium of sparingly soluble salt. Now, salts are classified on the basis of their solubility into three categories. The first category is, we classify salts as soluble when the solubility is greater than 0.1. If the solubility is between 0.01 to 0.1, we classify those salts as slightly soluble. And if the solubility is less than 0.01, we classify them as sparingly soluble salt. So, when a sparingly soluble salt, as the name suggests, sparingly soluble, ions to banane nahi wala. When a sparingly soluble salt is dissolved in water, only a very small part of it is dissolves and dissociate into ions. In a saturated solution of such a salt, the ions, they remain in equilibrium with the dissolved salt. So let's take an example over here, students. If I have, let's say, a salt like AgCl in equilibrium, because it's a sparingly soluble salt, so it is in equilibrium with Ag plus and Cl minus. If I write the equilibrium expression, so equilibrium expression will be Ag plus into Cl minus upon AgCl. Please remember, students, AgCl is a sparingly soluble salt, and hence it's you can say that its concentration will remain constant. So K is a constant, AgCl is constant, it is replaced by KSP, which stands for solubility product. So KSP for this will be Ag plus into Cl minus. Let's say if the solubility for Ag plus is S, the solubility of Cl minus is also S. When you substitute that here, we get S times S, KSP is S square. Basically, if I have a binary salt, the solubility product for a binary salt will be S square. If I have a ternary salt is a salt which produces 3 ions. So PbCl2 in equilibrium with Pb plus 2 and 2Cl minus. If the solubility of Pb plus 2 is S, for Cl minus it will be 2S. When we write the expression for KSP, it will be Pb plus 2 into Cl minus the whole square. That is S into 2S square. So that becomes 4S cube. I want you, students, to find the KSP for the following salts, and if you have any doubts or any If you do not get the KSP values for this, please let me know in the comment section and I'll derive them for you. Moving ahead, we have applications of solubility product. One of the applications of solubility product is to find the solubility of the salt. But the second and the most important application is to find or to for the prediction of precipitation of a salt. Now, what exactly we mean by that? If I have the ionic product is the product of the ions of the solution. Students, solubility product is the product of ions, the concentration of ions in a saturated solution. I repeat, let's understand the difference. Ionic product is the product of concentration of ions in a solution, and solubility product is the product of concentration of ions in a saturated solution. If the ionic product is less than solubility product, so we know that the solution has not reached saturation, it's an unsaturated solution. If the ionic product is equal to solubility product, then we know that it has reached saturation. And if the ionic product is greater than the solubility product, so we have a super saturated solution, or in such case where the ionic product is greater than solubility product, we get precipitate. We can get questions on these, students. Very common questions आते हैं where they will tell you whether यहाँ पे precipitation होगा या नहीं होगा. आपको ionic product निकालना है या आपको solubility product के basis पे you can easily find कहाँ पे precipitation होगा and कहाँ पे नहीं होगा. And moving towards the last slide, students, we have what is called as the acid-base indicators or pH indicators. Now, students, I hope everyone has done titration. तो आपको पता होगा titration में आप indicator use करते हैं. So, organic compounds which indicate the end point of an acid-base titration by visual change. तो आपको पता है जब आप titration करते हैं, the moment there is a color change, आपको समझ जाता है yes. We have reached the end point, we have reached equivalence. Then the reason for that visual change is what is called as pH indicators. pH indicators, students, are also called as acid-base indicators. Now, I've written the most commonly used indicators here, students, which is phenolphthalein and which is methyl orange. Phenolphthalein is commonly used for the titration of strong acid against strong base, and the pH range for this is usually 8 to 9.8. The color changes from colorless to pink. Methyl orange is commonly used for the titration of strong acid against weak base. The pH range for the same is 3.1 to 4.5, and the color changes between red and yellow. So, students, this completes all the important topics that we have in equilibrium. I hope everyone will get value out of these, and please make short notes, and whenever you want to revise quickly before the exam, you can always watch this video. Students, thank you so much for your time, and this is Nitin sir, JP's Academy. Thank you so much.